Hi everybody, my name is Greg Maidment. We're out in Newell County at our Field Research Station for Carbon Management Canada, CMC. This facility was really brought together by Dr. Don Lawton. It started as a place to show CO2 injection best practices, but it's really turned into a world-leading research center for monitoring as well as CO2 injection. The purpose for us here now is to be able to combine as many different monitoring data sets to come up with a very comprehensive picture of what's happening in the subsurface. We've got surface seismic, downhole seismic, fiber optics throughout the whole facility, over 5 kilometers of fiber optics, as well as all of our monitoring equipment on the surface and down our injection wells. We've also been really lucky with not only the ability to be gifted all this technology for subsurface monitoring, but we've also become a world leader in emission monitoring as well. We've got one of only 2 dual cone mass spectrometers on site, which measures a live 3D image of all emissions passing through the site, so that we can combine that subsurface monitoring with anything that's moving up through the atmosphere. So we'll have a quick walk around. I'll show you everything at the facility and give you a little tour on how operations happen here at CMC. So we're in our control shack. Our full facility can be run and controlled from this computer, which we are lucky enough to be able to remotely log into from Calgary. All of our recording devices that are in the facility run through this computer, and then our other recording devices, the ERT, fiber optics, geophones that are downhole, the geodes, are all run from inside the classroom. So one of the main goals of the FRS, of the Field Research Station here, is information dissemination, sharing of information, collaboration, and general learnings around the process. So we have an on-site classroom to work through. You can see our second CO2 monitor sitting here, just for safety along the site. Inside the ATCO trailer here, we have a classroom for learning, for teaching, for working, as well as our technical room on the end here, which has all of our computer systems in it, the controls for the dual cone mass spectrometer, for the geodes, for the ERT, and any of our weather stations as well. So we have our CO2 tank behind us here. Currently we truck our CO2 into site. It's stored in liquid phase in this large tank here. It holds about 52,000 kilograms. To keep it all in liquid phase, we have our cooling towers behind it. Pushes the gas phase gas up one side, gas phase CO2 up one side, pushes it over at the heat exchanger on the top, and as it falls down the other side, it compresses into liquid CO2 so that we keep the pressure low in the tank and we don't have to deal with any explosive issues. So our CO2 stored in liquid phase comes down through our piping into our pump. Our pump pulls it out of the tank. We've got a variety of gauges, both temperature, pressure, as it comes out of the tank, and our emergency ESDs to shut down the equipment. The pump keeps it in liquid phase and pushes it down the pipeline to our next heater. So after we pull the liquid CO2 through all the piping, we bring it to this heater to turn it into gas phase. So the heater can heat the gas up to about 200 degrees Celsius. It's much easier to inject gas than it is liquid, much lower viscosity, easier to get it in the reservoir. So we want it to be in that gas phase as it hits the wellbore and as it is injected into the reservoir below. So this is our Christmas tree. This is our wellhead. The CO2 has come along through this pipe. It's now in gas phase, and then it's injected into the production tubing downhole into the Basil Belly River, our reservoir of interest. We have quite a few different gauges on the wellhead to measure, again, pressure, temperature, downhole, as well as that surface. And one of our CO2 monitors here, you can see we're currently at 240 ppm at this device. This is one of our safety shut-off features in case we have a leak out of the wellbore. This is our Geophysics observation well. We're only 20 meters away from the injection well. Down this hole we have geodes. around the injection zone, as well as 2 different fiber optic loops, one of them helical wound and one straight, so that we can observe any sort of temperature changes through DTS, any acoustic changes through the geophones and the DAS. This is our second observation well. We call it the Geochemwell. We're 30 meters away from the injection well now. We have open screens at a variety of reservoirs downhole so that we can actually take samples of gases that are moving through, liquids that are moving through the reservoirs, bring them up to surface for testing. So in conjunction with the subsurface injection and monitoring, we're also doing emission monitoring. So we have a dummy tank that we're using here to do methane releases from. We have a controlled amount of methane that's released from our dummy tank. Use the tank as the background for OGI cameras, for laser-based recording, as well as the dual cone mass spectrometer and any drone or airplane basis that comes and wants to test their technology. For this full cycle monitoring program, we have quite a few soil sampling sites all over the section of land that we're operating on. We also have quite a few water sampling wells at a whole bunch of different depths. So we can measure how the aquifer changes from 150 meters all the way up to surface. We've seen no changes. We wouldn't expect any changes, but we need to make sure that that's the case, and we need to see if there's any subsurface variations. So this is UFC's recorder behind us here that is doing operations in conjunction with the Vibe out in the field. We're collaborating with UFC on all of our surface active seismic. So we can see Malcolm operating the UFC Vibe in the background there, and just to the left of him you can see that dirt line, which is part of our trench that has our over 5 kilometer long fiber optic loop. We have a down and back in each direction for a full kilometer of fiber optics buried in the ground, and then it goes in and out of all of our wells. So on top of our down hole recording and our trench of fiber optics, we also have a continuous hawk system that's buried underground, that's reading for passive signals. It's reading for any sort of microseismic, any shifts, any changes in the subsurface. So we have a large array permanently laid out, taking these recordings, and we update them every month.
Hi, I'm Don Norton. I'm the director of CaMI within CMC, working with Greg and all the other group here, and we're today looking at the installation of DAS at our field site that you've seen on the tour with Greg. And we're specifically interested in using DAS as a monitoring technology. And at the site here, if you can see the screen here, we have a 5 kilometer loop of DAS optical fiber. We're sitting in here in the shack, and the loop goes out, and we have 2 observation wells, and we have DAS fiber, 2 types of fiber in observation well number 2. Helical wound fiber, which is shown in blue, and regular straight fiber shown in green. So it goes twice into this well, goes across into the second observation well, and then the loop goes into a kilometer-long trench, and we have the straight fiber and the helical fiber in the horizontal trench here as well. So we're looking at using the optical fiber for VSP measurements and surveys in the observation wells, which we're currently doing today. To look at the time-lapse response, the injector well, not shown on this diagram, but it sits between these 2 observation wells. So we're doing walkway VSPs and walk-around VSPs into these 2 wells. Here today is a time-lapse monitoring for tracking the CO2 that we're injecting from the injector well. And as well, we're looking at the response of fiber for surface seismic acquisition to record both reflections, and we've been working a lot on surface wave analysis, looking at the surface wave modes that Jan Detmer will talk about as a means of characterizing the near surface and looking at time-lapse variations in that as well. So from here we'll look quickly at the Interrogator, then we'll go outside and just look at how we connect these fiber loops together. Okay, so think back to the loop diagram we just saw. So this is the real-time display, waterfall display of all of the 5 kilometer fiber that we have. Remember, it goes twice in observation well number 1, so this first section is the helical fiber in observation well number 2. This is the straight fiber in observation well number 2, then the straight fiber in observation well number 1. Then we have a split. This is the straight fiber in the trench. This whole section is the 1 kilometer long helical wound fiber in the trench, and then the second half of the straight fiber in the trench. So we can, in real time, monitor the whole 5 kilometers on this display. But this will be recorded continuously while we do this VSP survey that is running here today. And then we'll be leaving this interrogator running so we can capture passive seismic events, particularly in the wells, as we're injecting CO2, as Greg showed you from the injector well description early on. So we're now outside at one of the junction boxes. It looks very busy, but here the fiber coming from the office is split into fibers running into the trench and into the wells. Each of the black cables is a bunch of fiber optic lines. You see where I'm pointing to now, there are 4 color-coded fibers coming out of one of the black cables. Each of those is a separate loop, so we have lots of redundancy. And it's really critical when you're doing the splices, that you hold on by the red tape on the backboard, that the splices are done very well, because we often get significant signal loss through the splices. But this was done very well, and we've been very satisfied with the performance of the box. You can see the fibers blowing around in the wind. That would actually induce noise, so that's why we keep this box sealed and closed whenever we're operating the system.
Hello, my name is Yichuan. I'm currently working as a postdoc researcher at the University of Calgary, and Don Lawton is my supervisor at here. So my project here will relate to the time-lapse DOTS data site, which is acquired at the CaMI site. And I will also use the Interrogator for my research.
Hi, I'm Marie Maquet. I'm a geophysicist working at CMC Research Institute. I'm mainly focusing on geophysical methods, so ERT and seismic data. And what I'm doing with the DAS is record continuous seismic data and to try to see how we can characterize the effect of the CO2 injection on the subsurface. So either if we can detect any microseismicity due to CO2 injection, or if we can image the CO2 propagation. One of the challenges we have with the DAS is it's a lot of data. We have 5 kilometers of fiber on the site. And it's going to be close to 2 terabytes of data every day. So we have to come up with a plan to try to work efficiently with this data, either by applying some machine learning data algorithm method to try to process those data as fast as we can and not having to keep 2 terabytes of data per day.